So, in the previous lecture we are having a study about the electronic configuration of lanthanoids. Also we are discussing about the oxidation states, variable oxidation states shown by lanthanoids. These are having the +3 stable oxidation state, +2 which lanthanoid shows +2 oxidation state are good reducing agents, and those which show the corresponding these are good reducing agent, and those oxidizing agent, and those which are have the presence of +4, those shows can be shown the +4 oxidation state are considered as good oxidizing agents. So here the next point, it is the color and spectra. The lanthanoids which are have vacant EF orbitals, which are have vacant EF orbital in their ionic forms, in their stable ionic form, this shows us the coloration, where as you all know about the EF transmission of electrons. The transmission, it is F subshell electron is transferred into another F subshell electron from the FF transmissions, which is responsible for the color of the ions. When we observe the M+3 ions, these are colored. Ions, these are colored. The calculation of the ions, or the formation of the conformation of the colors, it is on this basis of this table. Here, promethium is have in its trivalent or tripositive ion, it have 2 electrons. The electron configuration of promethium is xenon 4f5 6s2. From 4f we are having here the removal of the corresponding 4f3 61 4f5. In the 4f subshell we are having presence of 2 electrons. These 2 electrons can be deducted, can be minused from the corresponding 14 electrons. Total number of electrons, it is 14, which are present in the F subshell. 14 minus n is equal to 12 electrons. So it appears in the green color. In its solution, in its solid form, it appears in green color. Like this promethium, the corresponding helium, when you observe it, the atomic number, it is 69. Its +3 form have when you observe, so electrons are deducted from 6s and 1 from the F subshell to have the presence of 12 electrons on it. So it resembles the green color in its solid. It shows the green coloration in its solution also, NF electrons. Like this neodymium, when we observe neodymium in its +3 form, it have 2 electrons. In its 4f subshell remains 2 electrons are from here. We are having the presence of 2 electrons. So for 3 electrons, 4f3. So 1 from 6s and 1 from 4f are removed. Then we are having the presence of the corresponding 11 electrons by deducting it from the corresponding n. 14 minus n is the number of f electrons which are present. It have the 11 electrons, so it appears in pink color. Like this RBr, which have the electronic configuration as xenon 4f12 6s2. In its tripositive form, it have 11 electrons in its F subshell, so it can appear in the pink color also. This one is the color and spectrum. Spectra shown by the corresponding ions of the tripositive ions of the corresponding lanthanoids. Now the next term, it is the atomic and ionic radii and the lanthanoid contraction. When we observe, as all we know about the definition of atomic radii, the distance present between nucleus and the outermost electron present in an atom, it is known as atomic radii. And ionic radii the radius. It is the distance present between nucleus and outermost electron. The electron which is present in the outermost subshell in an ion. It is known as ionic radius. When we observe towards the atomic and ionic radius, we have to look at here closely. Suppose this one is nucleus and this one is the outermost subshell of the lanthanoids. As in this area we are having the one electron in its 4f subshell, so it is attracted towards the nucleus. As we move from cerium to corresponding phosphodiamium, one electron is also present in the same subshell, and we are having increasing one positive charge in the nucleus. So as increases the charge, we are having the increase in the corresponding attraction of the nucleus towards the electrons. Electrons are attracted towards nucleus. As we having increase in the number of electrons in the same subshell, we are having increase in the attraction of the nucleus, attraction of proton on electrons. As electrons are attracted towards nucleus, the size goes on decreasing. The distance goes on decreasing as we having addition of new electrons in the same subshell. And as we observe the shielding of F electrons, it is very poor. Due to poor shielding, due to poor squaring of FF electrons, as we having increase in the atomic number, we are having increase in the number of electrons in the same subshell, and with the increase in electrons, we are having also increases the positive charge of the number of protons in the nucleus. As the number of protons increases, as the electrons are added in subshell, same subshell, we are having increase in the attraction, and this increase in attraction of electron towards nucleus is responsible for the decrease in the atomic size or the ionic size of the corresponding lanthanoids. This one is a regular trend as we observe within the corresponding periodic table. As we move from top to bottom, the atomic size goes on increasing. As we move left hand to right hand side, the atomic size goes on decreasing. Alkali metals have largest sizes in their periods. Alkaline earth metals have lesser atomic size in the comparison of alkali metals. First elements are the largest sizes in their periods. Alkaline earth metals also have the largest sizes, but these have the less atomic size or atomic radius than the corresponding alkali metals. It means as we move from left hand to right hand side, the atomic size or ionic size goes on decreasing. This is the regular trend, and this regular trend is also followed by lanthanoids in there. So as we move from cerium to lutetium, the atomic size goes on decreasing, and this decrease in atomic size is due to the presence of newly added electron in the same subshell. So decrease in the attraction of the increase in the attraction of the corresponding nucleus to electron or outermost electrons, and we are having decrease in the atomic size of the atoms or atomic ionic size of ionic radii. This goes on decreasing as we move from cerium to lutetium. Lanthanum is also considered here. So this one is the lanthanoid contraction. As we are going here, we are putting a graph. Here the atomic radius and here the elements of the lanthanoid series. As we observe here, cerium's lanthanum's atomic radius is 103 picometer. Cerium is 102. After here 101. After here from cerium to lutetium, we are having a gradual decrease in the ionic radius of these lanthanoid elements. This one is simple here. As the electrons are added in the same subshell, we are having the decrease in their atomic size as we are having increase in the nuclear charge. As nuclear charge increases, attraction of electrons also increases. As electrons are attracted towards the nucleus, the added electrons are present in the same subshell, or addition of electron is conducted in the same subshell, which is responsible for the more attraction towards nucleus. And as electrons are increases, generally there is a shielding is present. When electron from the inner subshell is pulled outside the next subshell's electron, but here the screening or shielding of F electron is very poor in the comparison of D subshell, in the comparison of E subshell, in the comparison of P subshell. We are having very poor shielding or screening of F electrons, which is responsible for decreasing the atomic size, which is responsible for decreasing the ionic size, decreasing the ionic radius, decreasing the atomic radius. So we are having the contraction here of the corresponding atoms. Atomic sizes are much lower. When we observe a difference of these, the ionic radius difference, as we observe towards this cerium and the corresponding lutetium, we are having up to 20 to 21 picometers difference here. Not a marginal difference, but it have a difference in their atomic or ionic radius. So this atomic or ionic radius decrease or the lanthanoid contraction is responsible for the formation of chemical twins. As we observe in the third group, zirconium, after when we observe the lutetium, after lutetium there is presence of hafnium. The hafnium, it has the approximately identical size, identical atomic radius or approximately identical ionic radius, which is of zirconium. Zirconium is present at the 5th period. Hafnium is present at the 6th period. But we are having the contraction, the lanthanoid contraction is responsible for the smaller size. When you observe these atomic sizes or ionic sizes of zirconium and hafnium, these are approximately have the identical sizes. So this behaves or this presents as a chemical twin scale. This like this zirconium, hafnium, we are having other chemical twins which are not for your study here. But you have to remember that the decrease in the atomic size or the decrease in the ionic size, decrease in the ionic radius is responsible, or we can say the lanthanoid contraction is responsible for the formation of chemical twins also. Zirconium, hafnium. This one is the best example of the lanthanoid contraction. The atomic size or ionic size of zirconium and hafnium, it is approximately equal. So these are have the presence of the or formation of chemical twins. The properties of the groups, when you observe the third group, the chemical properties are same, but these present in the identical sizes. So these are behaves as chemical twins, zirconium and hafnium. This one is the lanthanoid contraction. But when we observe towards the metallic characters, firstly we are having a discussion about the metallic character here, or the magnetic properties. As all you know about the gadolinium, which is ferromagnetic at the 16 degrees centigrade. And after gadolinium, terbium, dysprosium, holmium, terbium, helium and ytterbium. Up to ytterbium, we are having the formation of the ferromagnetism. Formation of ferromagnetic moment at the lower temperatures. All these are up to the gadolinium, cerium, praseodymium, neodymium, promethium, samarium. These are behaves as the paramagnetic moment, and gadolinium at 16 degrees centigrade it shows the ferromagnetism. After gadolinium up to ytterbium, we are having the presence of ferromagnetism at lower temperatures. This one is the magnetic property of the corresponding lanthanoids, which is equal as the d block elements. The formation of paramagnetic moment or formation of the ferromagnetism, you will observe there about the d block element. There is iron, cobalt, nickel, which are ferromagnetic in nature. Like this, the gadolinium, terbium, dysprosium, holmium, erbium, thulium, and ytterbium. This also behaves as the corresponding ferromagnetism. This shows us the ferromagnetism in their natures. This one is explained as well as the explanation of the d block elements, where we are having a discussion about the corresponding magnetic properties of d block elements. These lanthanoids show the similarity in their properties, in their magnetic properties when we discuss it. Now, the corresponding application of these lanthanoids. Application. We are having color TV in our home. Generally, in our home, we are having the color TV, and the coloration is responsible. The coloration is formed due to the lanthanoids. The combination of them is responsible for the formation of color on the color televisions. Listen carefully. Here, the lanthanoid compounds are present in every household. Generally, when we observe, all our households having generally the color TV, color television tubes. It is present in the inside the color television tube. When electrons are bombarded, there, the metal and crystal lanthanoids, certain crystal lanthanoid compounds, generally they have their range. They can emit the visible range towards our eyes, which is having a large light over a small wavelength. Therefore, inside the inside surface of the television tube or computer monitor is coated with tiny particles of three different lanthanoid compositions to give three colors that make the coloring image. For example, we will observe the mixture of oxides of europium and yttrium. Oxides of europium and yttrium. Either the oxides of europium and yttrium. This one is the mixture. Oxide of europium and oxide of yttrium. These are mixed, and they releases an intense red color when bombarded with the high energy electrons. This shows us the formation of the red color. The optoelectronics applications are useful of lanthanoid ions, as these are active ions in luminescent materials. Luminescent means prakashmay, tejomay. Lanthanoid ions. When the most notable application is the ND-YAG laser. ND-YAG, what is it? It is the neodymium dropped yttrium aluminium garnet. Neodymium laser. It is neodymium yttrium neodymium dropped yttrium aluminium garnet. This one is the ND-YAG, neodymium dropped yttrium aluminium garnet. Also erbium dropped fiber amplifiers are significant devices in the optical fiber communication systems. Optical fiber, as we know, optical fiber it have the presence of erbium dropped fiber amplifiers. Amplifiers which are useful for increase the noise there. You are having increase in the voice there. Lanthanoids are used in hybrid cars, superconductors and magnets. These are some uses of the corresponding lanthanoids. These are applications where lanthanoids can be used there. So this can be studied in the corresponding lanthanoids. Up to lanthanoids, we are having a discussion about these applications. We are having the discussion about the magnetic properties. We are having the discussion about the color and spectra here. We are having the discussion about the lanthanoid contractions, which are responsible for the formation of chemical twins. So these are the lanthanoids. Generally, these are the lanthanoids which are metals. These lanthanoids metals are very useful in the corresponding formation of various materials which are having the use of magnetic properties or magnetic moment of it. And nowadays we are having the various uses of the lanthanoids. But generally, when we observe, the lanthanoids are soft metals. Exception is present also there. But generally these are soft in nature. These are having the formation of corresponding white color, soft metals or silvery white. Generally lanthanoids shows the properties like some lanthanoid elements show the properties like calcium, some shows like the aluminiums, some behave like aluminiums. Up to gadolinium we are having the reactions like calciums of corresponding lanthanoids, and after calcium from the gadolinium we are having the reactions of lanthanoids like aluminium, or they behave like aluminium elements. So these are the lanthanoids. We are having discussion about the lanthanoids here. In the next lecture we are going to discuss about the actinoids. Actinoids which are having the series of 5 elements. In the transition and mineral transition elements, we are having a discussion about the lanthanoids here. In the next lecture we are going to study about the actinoids, which are a part of actinum series. Actinum from actinum 89. We are having the presence of actinoids. These can be studied by us in the next lecture. So